So welcome everybody. Before starting this presentation, I just want to thank once again all the members of the jury for accepting to evaluate this work, and also for being here today, especially physically given the terrible circumstances of those days, and as well virtually, of course. So I will now present my PhD thesis work, in which we were interested in the functional specialization of medial temporal lobe, as well as the hippocampus and hippocampus internal organization. And we studied this from the point of view of the representational approach. So this presentation will follow a traditional frame. I will first introduce our theoretical model and the hypothesis which we investigated. I will then present our experimental contributions, starting by two methodological validation studies, one functional neuroimaging study and one neuropsychological study, before discussing those results. So, starting with the medial temporal lobe, well, located at the medial face of the temporal lobe are mainly the hippocampus, here in blue, and parahippocampal gyrus, here in green, of which the most anterior part is called perirhinal cortex, or PRC. And you can also see here in red the entorhinal cortex, or ERC. Well, those regions have been associated with memory processing for a long time, and at first with modules or systems of memory. And in particular, the hippocampus has been associated with episodic memory. So episodic memory is the memory system for all personal episodes and events. In contrast, semantic memory, or the memory for general knowledge and facts, has been associated with more lateral and anterior temporal cortex. Then, memory processes were identified and described, and in particular, recollection. Recollection is the central process in episodic memory, as it is the recall of a contextualized and rich event. And this process relies on a distributed brain network, but centrally on the hippocampus. In contrast, familiarity memory is the feeling that a stimulus has been encountered before without recalling the encoding context. And familiarity relies on perirhinal. But instead of this process view, more recently, a different functional organization has been proposed with the representational-hierarchical model, or RH model. This model mainly stems from the observation that information is represented in different manners in the brain, and in particular, in the most posterior regions of the ventral visual stream, that is in the occipital lobe. Information is represented in the form of very simple perceptual features, such as black and white lines, simple shapes, and color, for instance. Then those representations assemble to create more and more complex representations in a posterior to anterior axis. Now, those representations enter the medial temporal lobe at the level of the perirhinal cortex, where the complexity is that of objects and faces, and these kind of stimuli which we gather in a category termed entities. So entities are basically objects with no context behind them. At the highest level of this hierarchy is the hippocampus. And the hippocampus integrates those entity representations with more complex representations in which there's contextual details, time, space, and so on. And those representations are such as episodes or scenes, for instance. Now, this increase in the complexity of the representations is conceptualized as representational dimensionality. Now, the key point of this model is that the representation, and in particular, the representational dimensionality of a representation, is the key factor that determines the engagement of one of those regions in a given cognitive process. Now, further in this view, it has been proposed that we can break down cognitive processes, and in particular memory processes, into operations and representations. So, if I take back recollection, recollection is a recall of a rich and contextualized memory. So the operation here is a reconstructive operation, which we call pattern completion. The representation involved in recollection is a high dimension of representation because it involves a context and associative information. So based on this breakdown, what we know is that the hippocampus is engaged in a pattern completion of a high dimensional representation. it's actually recollection. And in contrast, the strength angle recognition, which is the operation involved in familiarity memory, for low-dimensional representation involves perirhinal cortex. But what we don't know is which of those regions is going to be involved in pattern completion of a lower dimensionality representation, such as an object, or in a strength angle recognition of a high-dimensional representation, such as a scene. In other words, which of the operation or the representational content determines the engagement of those regions in a given cognitive process. So to answer this question, it has been proposed to use those visual patches, as you can see here on the right, during a recognition task. And we ask participants to reconstruct mentally from memory the original images. And that measures pattern completion. So by using scenes and objects, for instance, we can measure pattern completion of high and low dimensional representations, respectively. And it has been shown that it has been found that the hippocampus was more engaged in a pattern completion than in the familiar judgment of the patch of the image, if the image was a scene, but not if the image was an object. And that suggests that the involvement of the hippocampus in recollection is determined by the high dimensional representation and not by the, rather than by the pattern completion operation. So based on this result, we hypothesized that in contrast, perirhinal cortex should be engaged in pattern completion of lower dimensionality representation. And in contrast, strength angle recognition of high dimensional representations should involve the hippocampus. And also, this pattern of engagement or specialization should be fine for any operation performed on the same kind of representations. So in our work, we had three main objectives. The first was to characterize more finely the patch protocol. So I'm going to explain that in a minute. Second aim was to investigate the predictions of the RH model using functional neuroimaging. So here we wanted to replicate the result which I just presented. We wanted to see whether we can generalize it to other operations. And finally, we wanted to study the long axis of the hippocampus. The final aim of this work was to investigate hemispheric specialization from the view of the RH model. So the general apparatus used for measuring pattern completion like reconstruction is to present those visual patches here. And we ask participants to reconstruct from memory the original images. So that came with two major questions for us. The first was, actually, pattern completion is the operation involved in recollection. But recollection is larger than pattern completion. In recollection, there's also the retrieval of contextual details, and there's the mental time travel feeling, and so on. So we wanted to know whether we can measure actually pattern completion without the participants resorting to recollection or trials. And second question was, does pattern completion rely on memory representation, or can it be performed with merely generic representations? So in a first behavioral study, we used a wall item condition here, and as you can see, patch condition where patches were built in this way. So they display limited portions of the original images. We had scene and object images. Now, in a wall item condition, we used a traditional remember node paradigm. So participants during the recognition memory task are asked to indicate whether they had a feeling of recollection, a feeling of familiarity, or whether the stimulus is new. Now, in the case of a recollection answer, that is a remember answer, we then used a justification procedure. So we asked participants to describe what made them answer remember, and we then rated in a double judge procedure those descriptions. In the patch condition, we used this reconstruction instruction. So we asked participants to reconstruct from memory the original images. And they can also judge the patch as familiar or as new. Now, in the case of a reconstruction answer, we then ask them whether they had a feeling of recollection during the reconstruction. And for each recollection answer, again, we used the justification procedure, the same as that. So first of all, the hits and false alarm rates showed no floor or ceiling effect. So it suggested that although the task is easier in a wall item condition than in patch queue condition, participants performed the task properly in both conditions. But what we were interested in was a rate of recollections amongst the reconstructions answers. And we expected to find reconstruction trials without recollection. And we actually found that the majority of the reconstructions occurred without proper recollection occurring. However, a significant amount of recollection occurred during the reconstructions, as you can see here. And the rate, the proportion of recollections amongst the reconstructions was highly variable between participants. So in study 1, we found that visual pattern completion can be performed without recollection. However, recollection and pattern completion did co-occur in certain trials. And this was crucial for the instructions we used in subsequent fMRI study 3, where we really needed to dissociate visual reconstruction from recollection. In a second behavioral experiment, we wanted to test the effect of exposition to the wall image on image reconstruction. So basically, we wanted to assess the contribution of memory representations to patch queue reconstructions. For that, we used a very different paradigm. This is an imagination paradigm. So we presented those visual patches and we asked participants to imagine what could be the rest of the image, but they had never seen the wall image before. And in each trial, when they had done so, we then presented the actual wall image and we asked them to rate how similar this image is to what they had just imagined. Now, because this relied on a subjective rating procedure, we also included some objective rating trials. So here the task is the same, but we asked participants to describe verbally what they had imagined. And again, we recorded those descriptions and we rated them in a double judge procedure. Now, importantly, in both kinds of trials, there is an exposition to the wall image, and that was crucial because the images were repeated throughout the experiment. So that was intended to provoke an encoding of the wall image, and so we predicted that that would be accompanied by an increase in the similarity between the imagined image and the wall image. Again, we had scenes and object images. So we did find an increase in the similarity with successive presentations of the wall image. And that was the case for both the objects and the scenes. There was an interaction showing that the objects had a steeper increase than the scenes. Now, those subjective rating results were confirmed by the objective rating results. So in study 2, we found that patch queue pattern completion does rely on prior stimulus exposition, which we interpret as meaning that it relies on memory representations. And that, importantly, was the case for both the objects and the scenes. Now, having characterized more finely the patch queue protocol, we then wanted to investigate the predictions of the representational hierarchical model using functional MRI. For that, 51 participants first underwent a visual discrimination task, in which they saw 3 images and they had to match one of the 2 images at the bottom with the image at the top. In one condition, all the stimuli were presented from the same viewpoint, whereas in another condition, all the stimuli were presented from different viewpoints. Again, we had scenes and object stimuli, so we had 4 experimental conditions. Now, this task was also the encoding for subsequent recognition learning tasks. We then divided the sample into 2 groups. The first group underwent the patch queue reconstruction paradigm, where they saw those visual patches, and we asked them to reconstruct the original images from memory. And we were particularly interested in those reconstruction trials, which were intended to measure pattern completion. Now, the other 25 participants underwent the wall item recognition task, in which we used a traditional remember-know paradigm. And here we were more interested in the familiar and new judgments trials, which were intended to measure strength signal recognition and strength signal rejection, respectively. So in this protocol, we had 3 memory operation and 1 visual perception operation. And those 4 operations were measured with high-dimensional representations, so the scenes, and low-dimensional representations, the objects. And we predicted that the hippocampus would be more activated for the processing of high-dimensional representations, whatever the operation, and in contrast, perirhinal cortex would answer preferentially to low-dimensional representations, again, irrespective of the operation. So first of all, we chose a reduced field of view, which was centered around our regions of interest, so that we could optimize the signal in those regions. Now, in terms of analysis, we first segmented the hippocampus and parahippocampal gyrus regions on all participants' native scans, so with no normalization. And for that, we used the Ashley segmentation scheme. We then divided the hippocampus into 3 equal length segments manually, the anterior, medial, and posterior hippocampus. And we did the same with the parahippocampal gyrus, where the entire segment was used as a perirhinal cortex region. Now, we also performed manual segmentation based on anatomical landmark, so that we then performed a region of interest validation analysis, and that yielded no difference in the response. So first of all, we replicated the previously reported result that the hippocampus was more engaged in pattern completion of scenes than objects. In contrast, perirhinal cortex was more engaged in pattern completion of objects than scenes. And importantly, this effect was found in the 4 operations. One surprising result, however, is the absence of effect of representation in perirhinal cortex for strength signal rejection specifically. In addition to the region of interest analysis, we also performed whole brain analysis. So we compared activity for the scene to activity for the object in all the tasks. And we found significant activity in the hippocampus for the scene minus object contrast in the 4 tasks. So having shown that, we next wondered whether the same region of the hippocampus had been activated in all 4 tasks for this contrast. So we performed a conjunction analysis, which tests precisely this hypothesis. And we found a region located in the right anterior medial hippocampus, which had answered to this contrast significantly in all 4 tasks. Okay, so in study 3, we did find a scene specialization in the anterior hippocampus, and we found entity specialization in the perirhinal. Now, importantly, both specializations were found across operations, and that was one of the central hypotheses of the representational approach. In addition, we showed that the scene specialization in the hippocampus was located precisely in the anterior medial region. Now, one surprising result was in the strength signal rejection condition, there was no effect, no specialization for entity processing in perirhinal cortex, and that was unexpected. That could be explained by the 2-week similarity between the targets and the foils in the object condition of the recognition memory task. That's one possible explanation. Now, at first, we did not find any effect of viewpoint in the matching task in the hippocampus, and that was unexpected. In contrast, we had this effect in perirhinal cortex for entities. We finally found this effect, but only when controlling for task performance. And that was very exploratory. Okay. Last aim of this work was to investigate hemispheric specialization from the view of the RH model. So in memory, the left MTL is usually associated with verbal memory, generally. And in contrast, visual memory relies more on the right MTL. So in this context, because in this literature and in our work, we usually use this kind of perceptual stimuli to manipulate representational content, and because this relies on perceptual complexity and perceptual ambiguity being the degree of feature overlap between stimuli, We thus hypothesize that this may rely specifically on the right MTL, and there is evidence in the literature suggesting so as well. We thus recruited patients with temporal lobe epilepsy, TLE, who underwent surgery of the entire temporal cortex, either on the left or on the right hemisphere. So we had 12 patients with left and 8 patients with right TLE, as well as 38 control subjects. Now, those patients do not present with amnesia, but they have slight memory impairments. And in particular, that was the case more strongly for the right TLE patients, unsurprisingly in visual working memory and visual memory. However, they do not have any intellectual ability or general cognitive ability impairments. And that was crucial for us because any perceptual reasoning that is low-level perceptual ability impairment would have an impact on the task we used. So again, we used a matching paradigm. And in addition to the scene and the object images, we also had those buildings. So we had 3 levels of perceptual complexity. Again, in one condition, all the stimuli were presented from the same viewpoint, and we also had a different viewpoint condition. So first of all, we found that patients with left TLE performed just like control subjects, and they had the same pattern of results. In contrast, patients with right TLE had an overall decrease in the accuracy when compared with the other 2 groups. And in particular, in the case of different viewpoint presentation for buildings and scenes, they did not exceed chance level anymore, unlike the other 2 groups. So we did find impairments in right TLE patients specifically. And those impairments were actually exacerbated by perceptual ambiguity. However, with those data, it is very difficult to exclude a task difficulty explanation because the effect found here is an overall decrease in the accuracy, whereas the pattern of result is the same between the RTLE group and the other 2 groups. Overall, those results question the other kind of features that contribute to representational dimensionality. So the first aim of this work was to investigate the patch-tree reconstruction paradigm. And we found that our results suggest that recollection can be divided into a representation and an operation. And that using the patch-tree protocol, we can measure pattern completion while varying dimensionality. So using this paradigm, we found that pattern completion of scenes relies on the hippocampus, whereas pattern completion of objects rather relies on the perirhinal cortex. And this pattern was found for all operations we investigated, including non-memory operations. Taken together, those results are in favor of the representational approach. Now, we also studied the internal organization of the hippocampus. And first, regarding the long axis of the hippocampus, there is evidence for different scales of information representations along the posterior-anterior axis. And we found that the scene specialization was specific to the anterior region of the hippocampus. Now, those results accord with a broad-to-sharp model of the internal organization of the hippocampus, where scenes can be regarded as global spatial information, which is a kind of broad information which relies on the anterior hippocampus, whereas posterior hippocampus would process sharp information. Now, we also found the scene-specific region in the hippocampus to be located in the anterior medial portion. And that is very interesting in the light of very recent results, which show different patterns of cortical connectivity within the hippocampus that varies including along the long axis, but also along the transverse axis of the hippocampus. And it was also identified that one region has a very particular pattern of cortical connectivity within the hippocampus, and this region precisely matches the region which we identified in the conjunction analysis. Now, the other axis of brain organization which we studied was hemispheric specialization, and we found visual discrimination impairments in the case of right MTL damage specifically. That questions, as I said, the other kind of features that contribute to representational dimensionality, And in particular, an interesting lead is conceptual features, and there is evidence in the literature suggesting so. And we are currently building an experiment to investigate the effect of conceptual ambiguity again in patients with unilateral damage. That also questions how the hippocampal broad versus sharp representation model can be applied to those conceptual representations. And that also questions how those principles of organization can be applied to language, creative thinking, or also problem solving, all domains which have been associated with the hippocampus as well. I just want to finish with a couple of perspectives. So the first is most posterior regions of the ventral visual stream. So in this work, we focus on the medial temple. However, the representational approach also has predictions for more posterior regions of the ventral visual stream. And in particular, those should elicit a specialization for low-dimensional representations, but again, for any operation. So in other words, we should find memory for very simple information outside the medial temporal lobe. And the last lead I want to mention is the early detection of Alzheimer's disease cognitive changes, because there is evidence for an entity processing decline in those early stages, and that was related to the volume of the perirhinal cortex as well as anterolateral entorhinal cortex. It has been suggested as well that we should evaluate entity representation without sticking to one domain of cognition. And I believe this is well supported by our results, since we showed representational specialization across operations, including for entities in the case of the perirhinal cortex. With that, I want to thank you all for your attention, and I also want to thank all the people who have been involved in those 3 years of work, as well as all the structures and institutions here.